data structures that are in the image format that are dealt with by the system are aligned. We make an attempt to make sure that we...
What do you mean by natural boundary?
Yeah, natural to what?
Bytes are on bytes in the file. If you look at the file as a view of mapping that directly onto a piece of memory that's, say, page line, that every piece of data in that file will be, that's metadata to the image, will be naturally aligned.
Naturally to what?
To its own address.
Right.
It's zero mod, whatever the address size or the data size is. Bytes are on bytes can be at byte offsets. 16-bit words can be at 16-bit offsets in the file. 32-bit things can have to be 0 mod 4. You don't have to copy things into one structure so you can access them.
Okay, I thought for a moment you might be talking about something else which had to do with image layout versus some sort of page size issue.
Well, that's later.
Okay, put it on the second. We could get to it later.
Let me go down the list here. Actually, the image format, as it's laid out in the file, is such that it's on the file system allocation boundaries, and the image header does say what it thinks the page size is, right? So there is a question about how big, what you end up with is you have a section, and it's so big, and the end of that section may be longer or shorter on some machines, depending on what the residual part of the page size is. Now, one of the things we're going to do probably to make sure this all works real portably is we're actually going to try to get the system to run with a page size different than 4K bytes.
An issue I've seen in practice is that you have two sections that are butted.
We don't do that.
Okay.
That's gone. They're separated and they're on the disk allocation boundary.
Even if they're on the disk allocation boundary, you can still get into problems if the empty space between is too small.
No, because we don't do that.
Okay, as long as
don't do
you're
that.
trying to put in large separations.
We know that the rest of that section is 0 if you page it in. We know where that ends. The pager knows how to page in partial pages. Is what you're talking about. Yes, sir.
We're talking partly about that and partly about the deals that sticks in my head is, without that being named, somebody came up with a executable format in which they wanted to make sure that dereferencing 0 blew up. And so the first 2K was defined to be not accessible, and your text started at 2K, which worked real fine until you had a system with a 4K or 8K page size.
Okay, I could back up a little bit. In general, we don't map. By default, we do not allow an image to be at 0. And in fact, the lowest we would like to put an image is 64K because of protection boundary problems, right? With pages. However, you can absolutely use the pages starting at 0 if you want to, because you might want to build an emulation system that has to run programs that did start at 0, like x86 programs, right? Where you really want to start at 0, 16-bit programs, you don't want to access things at 0. So in that case, but by default we don't do that. The image format is such that we try to minimize and localize any fix-ups we have to do, for instance, for DLL loading. We support resources with the same capabilities as OS2. Let me explain what resources are. Resources are sort of things that you can stick in an executable that can be selected with a call to some library routines by an index or an ID. So typically what people put in as resources is things like they might put a certain font in. You might have a font selection in the image where you can select different fonts for whatever it does, and it would then select that stuff out of the image based upon a key. might be a program that's been internationalized. You've actually replaced the resource with whatever the messages that it wants to put out. It might be the bitmap of the icon that this thing displays, where this is customizable by a user using some kind of a edit facility that says, well, geez, when I run my favorite program, I don't like the icon that it puts up. I want to put up a different icon. So there's a way to paste those in. The only thing that occurs in the privilege mode of execution as far as activating an image or mapping it is that we map the header, we look at the header and examine it to see that it looks like an image, and then we use the information that's in the header to map the whole file to the address space, and that's all we do in privilege mode. So it's more or less of a map file, right? Which means, by the way, when we map it, we take care of all these things about having partial pages. So we know about all those things. And then when we actually start running the image, in user mode is where we do all the binding and all the fix-up. Right, so that's just done in the normal, we don't have to screw around in privilege mode doing that stuff. The entire image is mapped. The header's mapped, the code's mapped, the data's mapped. The fix-ups are mapped. You read the fix-ups, somebody has to read them anyway. The fact that they're there, you just go get them. I talked about the binding being done in user mode. And we actually do binding. The binding, what you have in an image is you have a set of exports and a set of imports. And of course, the binding is satisfying all the exports and imports. And when you do that, you don't want to spend a lot of time looking up strings, so we use a method called hint indexes. And when somebody binds to something, when you link something, you actually say, here's what's going to be in it. It resolves all that stuff, it keeps a hint, and if the hint index works, fine. If it doesn't work, then we'll go do a string lookup. But basically, you don't have to keep things in sync with respect to, I reference index 5 in that image. You actually can go replace the DLL with another one where it became 6, and it will still work. It will just take a little longer. The DLLs that we provide with the system, which you could think of as being things like the C runtime library and some of the other things, we tend to lay them out in memory so they're mapped at a preferred address, which means that we want to map that thing there if we can. If we can't, then we will have to relocate that DLL dynamically somewhere else, and we can do that too. But for the fastest activation, you want to sort of stay out of the way of where the DLLs are. This is really sort of an extension of COF, cleaning up some things. It's more of a COF-like structure than it is some of the stuff that was in the PC. The PC executables weren't very directly mappable as files, so you could map them into the address space and directly page from them. So that's kind of wraps up what I have to talk about. The next guy to talk is Mark Lukowski, and he's going to talk about the Win32 base APIs. Do the slide, okay?
Yeah, if you want to give them to her, let me I'll have Madeline do it.
All right. This is the set of slides.
Okay.
All right. This is not.
You didn't use those?
No.
Okay. Do you want to hang on to those, or do you want me to hang on to all of them so you get to sit back?
You can.
We're going to talk about the Win32 base APIs, but I can also cover any kind of questions you guys have about POSIX and the whole POSIX server issues. I don't have any slides on that, but I did a lot of the original work, and if you want to understand anything about it, let me know. The base API includes all the low-level operating system functions needed by GUI apps. It's basically all APIs not associated with window management or graphics are part of the base API. This includes tasking, process and thread APIs, memory management, synchronization, I/O, and other miscellaneous APIs, some holdovers from Win16. The base is implemented mostly as a stateless DLL or shared library directly on top of NT. There's very, very little of the base implemented in the server. We'll into that in just a second. But where there's state that's shared between multiple processes, the Windows server takes care of those APIs. And finally, the API set is based in its entirety on the Win16 base API. There are a few things taken from OS2 and LAN Manager, like name pipes and mail slots and some of the async I/O, but basically it's an extended Win16 with a few of the networking extensions. Structurally, it's pretty simple. There's the Win32 application program, and it makes all Win32 calls by calling into the Win32 DLL, and this is just a standard procedure call interface. Then from there, the Win32 DLL exports base, user, GDI, and the console API. So all Win32 APIs are bound into here. Once they get into the Win32, yeah. GDI is the graphics. I don't know what the D and the I stand for.
Device interface, graphics.
Graphics device interface. And user is the window manager. So there's base, which is the traditional operating system sort of functions, and then the window management functions, and then the graphics functions like line drawing and that sort of thing.
So in general, you're referring to your window manager as the Windows as a user?
Yeah, it's called user.
I'll talk more about that.
Scott will talk about user later on, and then there's going to be another presentation on GDI. But anyway, so all Win32 APIs are exported up here. Once they get into the DLL, there's basically three types of APIs. There's APIs that are done entirely in the DLL, in which case you're just making a procedure call, the DLL is doing a little work, and then returning information. And examples of that are Win16 has this concept of a local atom where you can store a string and refer to it using a 32-bit handle, basically. So that's all local state that only affects your process. It's not shared anywhere, so it's done in the DLL. This DLL has some memory associated with it that when you bind to the DLL, you map the code and data into your address space, and that data is private to your address space. It's actually shared read-only, copy on write. So for the read-only portions of it, it's shared among all Windows users. And once you touch it, you get a private copy of it. So there's a large set of APIs that are done entirely in the Win32 without calling into NT for anything. Then there's the sort of APIs that are implemented by the DLL, massaging parameters and then calling NT. Examples of that are things like opening a file or reading and writing a file or allocating memory or some of these other sorts of things where Win32 just puts a user-friendly interface on top of the NT APIs and gives it the Windows look and feel without changing any of the underlying NT functions. The third class of APIs are those that are done in the Win32 server. And these APIs are done in the server because they create global state or effect global state. And examples of that are Windows has this global memory heap. It's called global alloc with the VDE share option. But what it is you can essentially malloc a piece of memory, and that memory is visible in all Windows applications at the same address. So the Win32 server maintains the heap structure for that pool of memory.
What's that used for?
It's used for some message passing, but you can use it for general shared memory if you want to. It's kind of weird shared memory where the sharers don't have to agree to share. It's really, you know, global memory, and you can allocate a piece of it. So
I'm just wondering how it fits into the security.
well, it fits into Windows. Is how it fits in. Yeah. No, there really is security on Windows. The Win32 servers does enforce security. So on this DDE pool of memory, there's actually multiple pools of DDE memory. So, you know, when one desktop is logged in under Fred and all the applications started by Fred have a pool of DDE memory. So your logon index will tell you which chunk of DDE memory, you know, you get to share with all your other apps. And then there are some facilities for transferring between the two through a special clipboard option or something. I don't know. Anyway, so other APIs that are done like that are the console API and a lot of the window management and graphics. That class of APIs are done by calling into the NT executive and doing an LPC remote procedure call over to the Win32 server. So what happens is the application calls into the DLL marshals the arguments into a piece of memory shared between the application and the server, and then calls the server with an API number and pointer to the shared memory. The server then does the API and replies back through the LPC port. For the base, it's like there's maybe 4 APIs that are done in the Win32 server, and the other 100 and some odd APIs are done entirely in the Win32 DLL. So that kind of gives you a feeling for how much you can really do in these DLLs and how little you actually go to the server for that sort of thing. For user and GDI, it's a different story because most of what they do is affect global state, like flipping regions and windows and that sort of thing. POSIX is real similar in structure to Win32, where you basically have your POSIX app and your POSIX DLL and then the POSIX server. The difference there is that just a much higher percentage of the POSIX APIs have to be implemented in the server because there's so much global stuff going on, like Signal. Signal says, geez, I want to, you know, throw something on the stack of another process. And there's all these rules about, you know, geez, are you in the same job control group, and does your PID match somebody else, and are you a zombie, and all that stuff. So the entire POSIX process structuring and relationships are implemented in the POSIX server. And any API that has to, you know, take a look at that that structure is done in the server. But things like I/O, or at least I/O to files, are done entirely in the DLL. I/O to pipes is done in the server because again there's global state that's being affected, and there's all sorts of rules about, you know, buffer full, buffer half empty conditions, and that sort of thing. But basically it's real similar in structure to Win32. So when we came up with the base API, our primary design constraint was that we wanted to provide an API that allowed simple migration from Win16 to Win32. So the API looks and feels like Win16, and to most apps it can really be viewed as a wide version of Win16. There's not a lot of random changes just because we're coming up with a 32-bit API. So the APIs have been preserved but widened, and we believe that you're able to share common code between the 16-bit code and the 32-bit code, where your pointers in 16-bit land will automatically be expanded to 32-bit, and you won't really have to think a lot about it when you're talking about the base APIs. unlike Win16, the Win32 base API is a complete API. In Win16, if you wanted to open a file or do, create a directory or something like that, you actually had to do an int21 to call DOS to do that operation. So Win32, given that it was going to run on non-DOS platforms, we ended up, having a formal create directory, open file, delete file API set, so that they could write a portable app and you don't have to rely on DOS. And that also lets us run on RISC and it lets us run on DOS and NT equally well. The API includes advanced features like the true 32-bit memory management, threads, map files, asynchronous I/O, synchronization, security, and exception handling. We also added long file name support to the API, so we don't limit anybody to the 8.3 DOS semantics, even though on DOS the applications are going to tend to run into fat file systems, where the file system, is still going to enforce an 8.3 structure, but as far as the API is concerned, it'll run equally well on long file name capable file systems like HPFS or some of the other ones being ramped up right now. We also exposed the 64-bit file pointers in the base API. So where the original Win16 set file pointer thing looked a lot like a Unix LC, we kept that same idea but added an optional pointer to the second half of the 64-bit seek position. So you could choose to use 32-bit file offsets and not restructure a lot of your code, but you could also use the 64-bit file pointers if you wanted to convert over to that real easily. The only other thing is for Win32, since it does have security, it's enabled when it runs on NT, but it's not functional when it runs on DOS. So the security parameters are ignored. The biggest change for the Win32 process model is that it allows multiple threads per process, and it has preemptive scheduling. In Win16, you could only get rescheduled when you called to pull for window messages, or actually called to yield the processor. But on Win32, it's fully preemptive, just like the underlying NT system. All threads are peers. Within a process, they can all see all of the objects and open files and semaphores that the process can see. They can also all create windows or do graphics or call any base API. So there's not a special thread like in OS2 thread 1 is special because if it dies, the process dies. And it's the only one that sees signals, but in Windows they're all peers. Again, scheduling is preemptive. We also have priority control. Processes can attach to DLLs either statically by the image is actually linked to a DLL, or at runtime they can call an API to load a DLL and look up the procedure as it points to the DLL. DLLs are given a chance to initialize whenever a process loads a DLL. We call it an init routine in the DLL, and when the process unloads the DLL, we also call termination routine inside the DLL. Win32 exports structured exception handling that Dave had already talked about. That's made public in this API. You can use this, the same way you use it under NT, catch exceptions and recover from errors or touching bad memory, doing your own pagers or whatever it is you want to do. The other thing that we've done here is all threads have a single.
Excuse me.
Yeah.
How's that supported on the low end of the DOS?
What? Structured exception handling? Well, it's not really. I mean, it's supported. The the same way it is on the high end. This is
Built in.
yeah, it's built in. It's built into Win32 on DOS. Win32 on DOS is a real operating system that really takes control of interrupt vectors and the exception handling stuff. So it's all there. Windows on DOS isn't like you can't just party on DOS like you can if you're not running on Windows. So you can't just go in and say, I'm going to take over this interrupt vector and not let the operating system see it. If you did that today on Win3 or Win3 not running in enhanced mode, you could crash Windows and you can cause Windows to hang. So it is a real operating system. You can't just think around like you did on DOS. Each thread has a single 32-bit last error word. So when you call an API that fails, this word is updated with the error status and you can call to get extended error information. So if you're looking at a multi-threaded app where they're all doing things, we don't have the Erno sort of problem where Erno you might have failed, but somebody else had just cleared Erno from a previous call. So we have this get last error API that when you fail an API, if you care about the reason that you failed, you can call get last error and get the information. Otherwise, you can just key off of the failing API and just ignore the fact that you've updated the cell.
The failing API doesn't raise an exception with you.
No.
Don't have that.
Well, it depends on how the API fails, and like if you're doing an API that's done entirely in the DLL and you pass it a bad pointer, you may or may not get an exception as a result of that bad pointer. It depends on the API. We're not going through the trouble and saying, hey, all pointers are going to result in an error of type access violation. You might see an exception as a result of passing a bad pointer. Just like if that API happened to be implemented in a C runtime, you would probably get an exception or get a core dump message rather than anything else. So I think that we're being semi-consistent that we're not raising exceptions always and we're not returning errors always. It depends on the API and whether it has to catch an exception so that it can clean up some stuff that it's halfway started. It'll catch the exception and you see the error as an error result code. If it doesn't have to do any cleanup and it's safe for it to take the exception and pass it on up to the caller, it'll do that. So it's not.
Did you go and change any things that were in the Win16 API to add exception? Do any of the functions that were in the Win16 API that didn't raise exceptions, do they now raise exceptions?
They can. What
You
is
pass in a
Windows?
bad pointer, certainly, but under enhanced mode, you would get the same thing. The default wouldn't be an exception you could actually handle.
Yeah, it would be something that would just kill the app, right? So, I think we're being consistent in that at least, we're giving you a shot at it. And in fact, before each thread starts, there is Win32 establishes a default handler at the top of each thread. So exceptions are always going to be handled by either the Windows frame-based handler or Dave mentioned the exception port that's a per process port. If you've completely destroyed your stack or any of the frame-based handler tables, Windows will see the exception through the exception port and cleanly terminate the application or keep it going, or, depending on what's appropriate for that sort of exception. The most significant change from Win32, of course, is the 32-bit flat address space, whereas all previous Microsoft systems were 16-bit segmented. This is the first 32-bit version of Windows. Memory is addressed using flat 32-bit addresses. This gives apps and DLLs access to 2 gigabytes of address space. Dave mentioned that we try to position the DLLs, system DLLs at least, in an area where they're not likely to conflict. What we're doing today is putting on at 1.5 gigabytes. We're starting our system DLLs there and going upward, but you know, that's just out of convenience. We could go at the top and go downwards, but we're trying to cluster them up at the top end of the address space today to leave the bottom open for things like Windows. Another thing that we're doing is as a default, we base user mode images at 4 megabytes. That gives people that are doing DOS emulations on top of Windows, it gives them the first megabyte to do the DOS emulation work, and so 32-bit Windows apps aren't going to collide with a DOS emulator that wants to be down at a megabyte. The memory management API is very, very similar to NT, in that it allows sparse sparse allocation with reservation and commitment. It gives you control over a page's protection. Where NT lets you set, you know, half a dozen or a dozen different page protection fields. Windows lets you set a page to rewrite, read only, or no access. So it doesn't support or require all the copy on write variations and execute read, execute write variations that NT has. So it's a subset of NT, and it's also presented a little bit easier.
It's a nice coincidence.
Huh?
It's a nice coincidence
What's that?
that NT and Windows have the same memory management model.
Yeah, isn't that interesting? Well, you know, OS2 has a real similar model here too, and you know, it's a real natural model. The thing that NT does that's a little bit different than all the other systems is the memory management APIs all take a handle to a process. So you can allocate and deallocate and change page protections in another process, and that's real foreign to a lot of operating systems. Even Unix doesn't have anything like that. But NT has this process handle associated with memory management APIs, so that from a server process you can affect a client's address space. So for the way that we do pipes on POSIX today is all the buffering logic and the actual pipe buffers are done in the server, and when you do a read or write that happens to go to a pipe, we go over to the server process, figure out the new pointers for the pipe, and do either a read or write virtual memory API directly into the other guy's address space. So we don't actually slosh data around through some LPC thing where you have to copy it twice. We just say, hey, I want you to copy this memory into that process at this other address. So that's the thing that's unique about the NT API is that it really is geared towards allowing these servers to have full control over their clients. Win32 supports a stripped down version of the memory map files that are present in NT. If I strip down, it basically doesn't have the option to let you map a file as if it were an image. Through the public API, you can map a file as a data file. We don't have the bit that says parse this thing as an image and expand it into my address space. That's something that applications tend to not have to do. It's more things like system loaders and system software wants to do. We want the Win32 API to be widely implementable, and that's one thing that could restrict guys a little bit. The other significant change from Win16 is that Win32 runs each process in its own separate address space, where under Win16 they all ran in the same address space. So all memory was essentially global memory. Win16 has a few different heap managers. They have local alloc, which basically lets you do memory allocation and movement and that sort of thing within a single segment. Global alloc, which lets you allocate and free memory that isn't bounded in a 64K region. Win32 implements both of these APIs, and they're fully compatible with the 16-bit versions, only they're not, local alloc isn't constrained to the 64K region. So they're really there for compatibility, but the distinction between what the two API sets are for has changed because of the 32-bit addressing. We also added a new set of heap APIs that take a heap handle, so you can create a heap and then do allocates and frees that are based on heap pointer. If you want to think that'll help your app. What you could previously do in Win16 is to get multiple heaps was change the value of your data segment and call local alloc again because it was just allocating out of your DS. So we formalized that concept with the new heap APIs that reduce the functionality from what you can do with local alloc. Win32 has a full set of synchronization primitives. It has the critical section, which is the fastest possible mutual exclusion object. It's for threads within a process. It's not a shareable sort of object. It's basically it's like an OS2 fast safe RAM semaphore, which is an in-memory test and set sort of thing, where if you get a collision, you make a system call to wait on a semaphore. So in the absence of contention, you can go in and out of these things in microseconds rather than having to call the system. But the downside is they're not shareable. We have the mutex, which is basically a shareable version of the critical section. But both of these are also recursive. We have event objects that may be shared. They can either be automatically resetting or manually resetting. And then there's counting semaphores. There's also a generic wait operation that you can wait on a single object or any or all of a set of multiple objects. You can also wait on process and thread objects, and those objects, waits on those are satisfied when the process or thread terminates. So the way you would do a C runtime sort of system API is you create the process and then wait on the handle that you got back, and when the wait was satisfied, the process is exited, and then you can exit code using another API. Then when you're all done with that, you finally close the handle to the process. These are obviously all ND safe. Better sound support is new in Win32. We've added a full 32-bit version of the full multimedia Windows sound APIs. This includes sampled sound, record and playback, and a MIDI sequencer. Sampled sound and MIDI sequences can also be transmitted through the clipboard and DBE and stored as resources. So you can store in your file, clips of sound. As a resource. That's another example of what Dave was talking about when he talked about resources. So I guess to summarize this, Win32 is simply a stretched version of Win16, overcoming some of the shortcomings of Win16 by adding things like threads, address space separation, security, long file names, and just kind of the general clean up and flushing out the API to make it a real portable API that isn't relying on DOS for That's all I have to say. Scott was gonna talk about the window manager next, unless there's any questions about POSIX subsystems.
What's CNT instruction that for the sound device room?
Well, the NT sound stuff is done in is a sound device driver. So I don't know if it's high octals to do certain things, but the read and write is the way that you pass data to it. And I don't know if the data is interpreted or not. I think that's
Can we get copies of your slides?
I have 10 copies there, so if I need to make more
That's enough
copies,
for 7 visitors here, so.
For something almost completely different, I'll talk about window management. We call it User, really kind of a great name. It started from user interface. User does window management, user interface such as menus, dialogues. Is everyone familiar with what a dialogue is? Dialogue is a little window that will come up. It's kind of a transitory window where you can input information into. All the little controls, we call these things inside of dialogues controls. There are supported types of windows that user supports. They're like button controls that say OK and cancel, and scrolling lists of items, and a couple of other kind of input fields. And it also user also was responsible for raw input, like keyboard and mouse processing, routing that to applications, and all messaging between applications. Most of user is primarily callback based. A lot of windowing systems are callback based, in that when the windowing system wants some event to occur, or wants to notify the application of some event that has occurred, it'll call back the application to tell it that event has occurred. And probably about 40% of the API for users is represented in terms of these callbacks, which we call window messages. Our primary goal, as with the rest of Windows, of Win32, was to make the APIs as simple a port from Win16 as possible. That was our first goal. And so where possible, we've tried to widen to 32 bits and make the porting process for ISVs as small as we can. The other big change, of course, was support for multiple preemptive threads of execution. Any thread inside of a Windows process, Win32 process, can create windows, do input processing, etc. We have an improved input model. What this means is an improvement from Win 16-bit Windows, which was a non-preemptive system. All input from device drivers went into a central queue, and applications took turns reading this input out of the queue. So if one of the applications that was reading input decided to go off and hang or read the disk or do some network activity or something that took a while, all the other systems would hang because they couldn't get input. So we've turned this into a model where a user can now interact and input into any application, no matter what the state is of any other application. The other thing one major change that we're adding is there's a lot of improvement in NLS support. NLS stands for Natural Language Support, and that's for our international customers, so that to try and make it easier for ISVs to create international versions of applications. Our goal for Win32 was to create a system where an ISV can make one binary, and by changing resources and other national or language-specific things can ship additional versions. One of the major differences here is something we call Unicode. You've probably heard about this Unicode conference. It's a 16-bit character set. Every character is 16 bits, and it supports all the characters of the world. We also remained ANSI compatible, and what we mean by ANSI is kind of a word that we use to mean the Windows 3 character sets. Windows 3 was an 8-bit character set, so there's 256 characters per character set, unless you go to Japan, in which case some of the characters were 1 byte, some of the characters were 2 byte. And everywhere you went, wherever you had a major difference in character set, just use a new character set. So that's what we call ANSI. So we are remaining compatible with ANSI for 32-bit applications because it's a significant porting effort to go from a 8-bit character set to a 16-bit character set, pervasive through your code. We're adding security. Dave's probably already talked about security goals. Again, the security parameters are ignored on DOS and are supported on DOS. User isn't really like a subroutine library where you make a function call with a known set of parameters and you get a known set of return values back. It's a little more complex than that, and then you make a function call and you can be called back with window messages 5 times before your function returns. And what window message you get called back with can be completely dependent on what the state of your application is. And that's kind of complex for ISVs to code to and to test to. And it's very important to be compatible with that, with message order. When we make a function call, an application has tested itself to be compatible with a certain message order back from the system, a window message order. And we absolutely need to retain that. So we're very compatible with Win16. Handles used to be 16 bits, become 32 bits. We have a couple places in the API where we are storing handles in 16-bit quantities. Window messages are comprised of a couple of fields under Windows 16. These fields are 16 bits, and so window messages now need to change a little bit, where we have this handle expansion problem. We need to fit them into the message parameters of window messages, and that affects 18 window messages out of a lot, probably about 150 window messages. The other place where we had size dependencies, we had a couple APIs where we actually set handles into things we call words, and words are 16 bits. And these people who use these need to change as well. Aged instances are replaced by HModule. That's something that is not too important. Multiple threads. As I said before, any thread can create window, do window management. When a thread creates a window, any window messages or any certificates for that window are only sent to that thread, the creator thread.
Can you pass ownership to another thread or another process?
No. You'd have to communicate the fact that you want to pass ownership and have the other guy create a window with the same attributes, so it'd just be a recreation. You can't pass ownership of an existing window to another thread or application. Windows created by that thread receive messages in that thread. Each thread has an automatic window message queue. When you get input from the system, keyboard and mouse device drivers, that queues up. And the queue is an automatic thing that the threads don't need to create explicitly, and it dynamically sizes.
Are there problems with overflow?
Yeah, there always is. We have to do things like, for example, we have to make sure that once we have a definite size, we're not going to dynamically size it forever. We have to make sure that if we get a down event, like a mouse down or a keyboard down, there's enough room for the up, so that you don't get into conditions where the system thinks keys are down or the mouse is down. We've had those problems for quite a long time.
Can you?
Yeah.
Go ahead.
Go ahead.
When the server side, what do you do about arranging priority of handling messages from different processes? How are they interviewed?
the application processing input gets a higher priority. And that, measuring that priority against other threads and handlers in the system is always kind of a fine-tuning process. I have not done that yet. So that's going to be, in the past operating systems, we've done essentially the same thing, and that is the application that the user is concentrated on, or the user is interacting with, or the thread that the user is interacting with gets a higher priority than the rest of the Win32 application code. Win16 applications could hang the system by not processing input. This was a major thing. It wasn't so bad of a problem on a non-preemptive system where if you didn't call yield, you'd hang the system anyway. On a preemptive system, this certainly isn't, or on a system that you want to be robust, it's clearly something you want to fix. What we're doing about it is allowing the user to switch to any application, no matter if that application is processing input or not, and input into that application, no matter what the application is doing. And finally, for hung applications, an application that isn't processing input by our considerations, doing either hung or doing something that's taken quite a long time, the user can still interact with it in a limited way. And that is, he can minimize it so it reverts down to an icon form, or he can close the application, or he can move it out of the way. Those are the sort of things you can do to a hung application. On Win16, there wasn't a common unified method or strategy for returning error status. We tried to do a better job of that on Win32. All available APIs return error status. Like Mark said, if someone passes in a bad pointer that is bad, points to invalid memory, it will raise an exception.
Hang on, will it return an error status or will it raise an exception?
So there's no way basically to range for one process, for one process that has one window, to gather up button clicks that are outside of itself.
Yeah, you can do that. And that's called capture, mouse capture.
Right, but when you move outside of a window, I think if what I understand is correct, if you move outside of the window and your mouse is up, you're not going to get it.
Correct.
That's right.
That's correct.
So you can't arrange to trigger something and then go somewhere else and click somewhere else and get that event back.
Right. That's a byproduct of changing to this different input model. Now, when we go down in the window, if the application happens to capture the mouse, then we're going to feed all the inputs in.
That's the easy case.
Yeah. Yeah. I/O errors and application exceptions are reported through GUI error dialogs. If you're familiar with those two, you would flash to a character mode screen and bring up a register dump. And we're going to fix that. Win32 is robust, designed not to crash. So if we do have if the system does go down, if one application can affect another application, it's a bug in the system. And the stability of another application is a bug in the system. We'll fix that. Here's some of the things we're doing with international support. First off, language IDs can be specified for constructs in the system which automatically sort, or which do sort. For example, we have things we call dialog box controls I was talking about earlier. One's called a list box, which contains a list of strings you can scroll through. And applications can just set this flag that says sort these things. And that's completely dependent on language and so in applications, the big model we're moving from is under Windows 3. There is one language and associated international settings for the whole system. And now applications can control their language settings independently, so they can display multilingual text, sort multilingual text according to the customs of that text, etc. Keyboard layouts can be switched with hotkeys. This is a request from some international users that they might want to switch between a keyboard and a French layout very easily. And we allow that with a hotkey. Keyboard layouts are customizable, so you can create your own keyboard layout. And we have support for input method editors, which are DLLs, which hook into the input stream for an application that allow, for example, Japanese users to input phonetic representations of kanji characters, and then this translator will go find the kanji character and stick it in the input stream.
How do you see the state of it while you're editing it?
It's a little status bar. And it's
At the bottom of the screen or at the window?
Well, that's a good question. In past systems, we've done both, and right now we're planning for it to be up on the screen. Okay. Another feature that we're adding is bit caching for Windows, automatic bit caching. Applications like CAD applications or applications that do really complex drawing take quite a while to draw. So you want those things to draw into a bitmap so that when the system asks the application to refresh that, it's an instant thing. So also allow you to start something drawing, put it in the background, and go do something else until the thing's finished. We've enhanced it a little bit, so when the application's on top of all other windows, it actually draws to the screen, so we don't go to this bitmap and into the screen. Another thing that we're adding, some customers have asked us for this over the years, is the ability to output both user interface and graphics calls to a different monitor. Applications, some uses of the system include two monitors or a dedicated monitor for something like someone doing CAD. You have this nice high-res monitor, and then you have your work monitor, and this will allow people to do that. As well, it will allow applications to take advantage of a given display hardware. If it can display multiple modes, the application can take advantage of that. That's it. Any questions?
Let's see. Because you're doing Unicode, how are you going to do your code to glyph mapping?
Kind of an interesting question. Right now we're looking at a nice tree structure that allows you to look at, say, the first 8 bits, okay, and you have 256 possible byte entries in a table, and they of course can be empty. And then if you have a hit in that table, then you go down to another 4-bit type table, and that again will take you to another level where finally you'll have these blocks of 16 32-bit handles that are your glyph IDs for whoever is supporting this thing. Could be a font driver or device or something.
And what do you do about things like tildes and stuff like that?
Tildes and stuff like that, well, they tend to be either characters by themselves or they can be composites. So,
Right, I guess what I'm asking is, so you're going to have composite support.
yes, absolutely. Mm-hmm.
Good question right now. There's some screens that support the ability to have one window of a particular depth.
Well, it really means what you're talking about hardware support for Z-ordering, right? I mean, we can order an application.
It's sort of a different issue. I mean, you know, given that you've got Windows, given that you're going to do essentially backlinks to it, you're going to keep track even when it's not on the screen. That can be fairly expensive if you're storing it at a depth more than what is needed.
Oh, I
So,
right. You mean color resolution? Like the guy only uses 4 tones. Hadn't planned that, but it's a good point.
Okay, now let's see, you're gonna put most of the stuff over, you're gonna put both the GDI calls and the user calls over, the GDI and the user stuff over in a separate server.
Most of it.
Okay. What kind of performance do you think it's gonna take for doing that?
Well, we did a lot of work on that early, and we still have more work to do. What we're looking at, Chuck can talk more about it, is particularly for DDI, caching attributes on the client side until we really need to call the server. Like, you set some attribute, you don't really need that attribute, so you do an output call. And we're thinking about batching those calls up so that we only cause a server call when it's absolutely necessary, when we need to return some object, for example, an object handle, we might need to call the server.
Have you guys looked at supporting both X and Windows simultaneously?
I've looked a lot about issues concerning that. For example, supporting Windows and PM and kind of primitives we'd have to share between them. We did something called Porthole, where we wrote Windows on top of PM, and all the issues regarding that we can talk freely about. I guess tomorrow we have a meeting at 9 a.m. and we can get into that in depth.
Okay, I'm here to talk about what we've done to GDI. That's what we call our graphics component and our graphics group. So again, like user is the name of the group, GDI is the name of the group. Again, this talk, like Scott's, was meant to be given to people who were very familiar with Windows, and so it really talks about differences between the new and the old. So if you need more details, ask, and I'm willing to fill in any details on what the old stuff was as well. Okay. This first slide concerns general changes across all of the interface, and they're very similar to what Scott talked about. Of course, our coordinates will be going to 32 bits, handles will be going to 32 bits, and counts and sizes can now be 32 bits, so we are getting rid of all the segment limitations that we had with DOS. Functions, return error indications, Scott covered that. Objects belong to one process. Okay, this is more of the security thing. So you can't create DCs and bitmaps in one application and expect that their handles are visible to others. Everybody's in a separate handle space as well as address space. Okay, these are some very specific changes, not particularly relevant. General here. So automatic brush origin tracking. This is a problem we had in Windows, and we're just fixing the behavior, so that's very relevant to this discussion. Applications don't load device drivers. That concerns security and client-server separation and all that. Since we're going to have a client-server separation, applications shouldn't be able to even see the device drivers. Someday they may be on different machines, so you have to keep those separated. Pack points and escapes, those are very specific changes to people writing Windows code. A big one that brings up a good topic is PELs may change from Win16. That is, the PELs that we're going to display on the screen may be a little different. And that's because, for the most part, our curves are changing under Windows. We had only ellipses that were oriented vertically and horizontally properly. And now we have general curves of many natures. And so we're changing our fundamental representation to Béziers. And of course, if you take an ellipse, crack it into 4 Béziers, the PELs are going to be a little bit different. Okay, that's the majority of the changes. Some PELs may also change just in line drawing, but this has to do with the fact that we're now keeping a fractional representation of the endpoints of the lines rather than just rounding everything to integer coordinates. So we figure that the change shouldn't be much bigger than going to a different display device, going to something with a different aspect ratio, Pelz would also. So, at some point, if you want to talk about exactly what Pelz we do draw, I'm willing to talk about that. We have a very specific imaging model now, and under Windows it was never really publicized what we did. Okay, new GDI features. So all the rest of these things are new things that we're adding. The first is that not only bitmaps, but all surfaces are considered to contain palettes. That is, any device you talk to has a color palette that it can represent. Okay, and we're also allowing that to be set with bitmaps. That is, when you say, I have a bitmap that I've stored on my disk, it comes in with a color palette. It tells you how to translate the indices in the bitmap into what real colors you're interested in.
So what happens when you render that palette onto, what happens when you render that palette into a window? It has already a full color map.
Okay, I believe the question is what happens when I split the bitmap into a window. Okay, I'm going between two surfaces. The bitmap's a surface, the device is a surface. I'm going between two surfaces with different palettes. I'll do translation and try to get the closest color match that I can.
I see. So for every color that's in that palette, we'll just try to, what kind of algorithm to use for color matching?
Well, okay, the algorithm we'll use, we
Actually,
attempt to be
let's talk
fast.
about it tomorrow.
So, what's that?
Let's talk about it.
Okay, well, fine. Yeah, but we try to do something fast, and we try to pre-calculate and cache all these things. Okay. So, and you're allowed, of course, on many devices to set your color palette, and we expect that's what people will really do when they have these nice color bitmaps. Set the palette, and then it's an easy translation. Okay. Brushes used to be limited to 8 pixels by 8 pixels. That isn't very useful on very high resolution devices. So now they can be any arbitrary size, choosable by the device generally for the stock patterns. Lines and text under Windows, they can only be solid colors. Now you can choose arbitrary brushes, get patterns, dithers, gray levels, whatever is interesting into lines and text. And again, that's a high resolution device thing. It's required these days. As I already mentioned, all of our curves will be based on Beziers. Absolutely everything is broken down into Beziers, and then depending upon the device, could be broken down further into lines and then sent out. We're adding paths to the system. These paths are used by applications in the form of, the application issues a begin path call, then a bunch of drawing orders, then an end path. At that point, a path exists for this particular drawing context, and that path can be used for stroking, filling, clipping, etc.
Can you get a region from a path?
You can get a region from a path. Yes.
Can you get the path that corresponds to the outline of the text character?
Yes. You do that by saying begin path, do some text out into the path, and just draw some text into the path, and then say end path, and then you can read it back if you like. So you can do all kinds of really neat special effects. Get your characters back in terms of Bezier outlines, map them onto spheres, or anything. But that's really up to the app. We're extending the transform capability. Windows only could do only scaling. It would have what we call the window viewport. You'd have some window in your logical space, a rectangle that you'd specify, and then you'd specify some viewport on your device, and appropriate scaling and translation would take place to map between them. But that was pretty limited. We're going to allow arbitrary linear two-dimensional transforms. So you can do rotation, shearing, etc. Okay. This is going to be added as one extra layer of transform that precedes the old transforms. And its default is going to be the identity, so that old apps won't notice this change, but new apps can have fun with it. There are a lot of things that get derived from adding new transforms. First off, it will be good if we can take our meta files and play them back through these arbitrary transforms. So on Metafile playback, you'll be able to specify one of these transforms, and it will be, you can play your little Metafile pictures sideways or rotated or sheared. You can also specify clipping. This will reduce some of the usability problems we've had with Metafiles. Allowing this new transform to be specified at that time. And of course, the Metafile transform itself is not metafileable. Kind of a funny issue. You have to worry about that. But whatever. Okay. Also, for consistency with the new transforms, we have a rotating bit blit. That is, if you say that you want to blit some image from here to there, and you have a rotating transform, well, the image gets rotated properly. Half toning, color blending. We're adding this to our stretch blit and rotate blit functions. The mix modes that they've had when pels needed to get combined or spread across other pels have been pretty primitive. Windows was originally designed for black and white devices, so it had and, or, ignore, that kind of color combining capability. Great for single bits, but not very good for color. So we'll be adding half toning and color blending algorithms. We'll be adding correlations. That's hit testing. You set a particular rectangle, and then you play your graphics functions through it, and we'll say whether or not any pels are actually turned on in that particular rectangle. So you can see if your mouse is pointing at some object or something. So we'll be adding device-independent color. The particular kind of model we're talking about is what we call calibrated RGB. That is, will allow the device, or will allow the applications to specify what kind of XYZ or tri-stimulus space they want to be in, and we'll do arbitrary linear transforms off of that space. So we'll say this device works in this orientation and has these limits, the gamut. And then the application can read that back or set the way it wants to talk about colors, and GDI will do all the translation in between. We'll still keep open the old channel, which is some RGB thing, which was really very device specific, so that old apps who use that get what they want, and of course it's also very fast. You don't have to do 3x3 transforms. Okay. In addition, we'll be adding CMYK colors that apps can set. People have said that would be useful. Scott already mentioned Unicode support. All of our APIs that take text strings will be duplicated. We'll add a whole new set, and they will take Unicode strings. So the application will have a choice. Printer control APIs. These used to be in, well, for the most part, these used to be in escape functions. We're just making them all clean APIs. And in addition, we're adding capabilities to change modes inside of documents. So if you're printing some long documents and you have a spreadsheet in the middle, you might want to go to landscape mode for a while, and then back to portrait mode. Okay, and finally, scalable fonts. These are also being added to Windows 3.1. This is TrueType for the most part, and we'll again have these features. So that's it for new features and stuff. But I'm willing to answer any questions you have about how the graphics works or what we do.
One of the earlier questions was about performance.
Yes, about performance of the client server? Yeah, that we expect to be in the 5% range. Okay, so 5% degradation from if we didn't do the client server split at all. Okay.
The device, what abstractions do you use? What calls do you make for graphic devices?
What calls do we make? We make very few. There's a bitlet, and then we allow the device to take over all the generalized levels of bitlet. That is, you can do a stretch blit, rotate blit, half toning, blending, if desired. Okay, but only the fundamental bitlet is required. And if they don't do these more advanced ones, that's fine. We also hand down a bunch of path calls, which are really stroking and filling calls. Will allow a device to do arbitrary geometric wide line stroking of paths, okay, or filling of arbitrary paths. But again, we'll take over the simulation of these things in GDI if the device can't do it. What we require of the device driver is being able to draw simple lines. Okay, and we'll construct things up from that. The next primitive, however, is filling of trapezoids. So something top and bottom are flat and two arbitrary vertical type edges.
What's required to calculate that?
Well, it's not exactly required, it's recommended. Rectangle filling is required. So if someone gives us a circle primitive and the device can't do path fills, then we'll send him down a clipping region that's supposed to be filled, but then the device actually calls back and asks, well, what's in this clipping region? We would prefer that the device ask in terms of trapezoids, enumerate trapezoids that make up the circle, because that's fairly efficient. But if the device is, well, not that smart, then we say, fine, we'll give you rectangles. And then finally, text output is required. So, and that consists of, well, very many different things. The application, or the device driver can ask for outlines that it will fill, or typically it will ask for little bitmap images and where to put them. So, pretty simple stuff.
What about the cutoff? Changing cutoff map?
Changing color maps. Yes, well, some device drivers will be able to export a palette change function. And if they do, then we'll take advantage of it. We will call and say, set your hardware palette to have this representation. Okay. If they can't do it, then of course we just ask, what is your representation? You know, what colors do you have? And then we will take care of most of the color translation before it gets to the device, except for things like bitblits. If you have a bitblit, then we'll say, here is the source bitmap. We want you to put this on your device, and here is a method you can use to translate. And then you can talk to this method and you can say, well, are you so complicated that I can't just get a simple array? You know, but if you can get a simple array, then you just have a little translate table and you blit as fast as you can through the translate table. You might also find out the array is trivial. Okay, otherwise you end up with a callback function where you have to take each pell that comes in, send it up, and we'll translate it and send it back to you. So it has a whole range of complexity.
Talked for a while about the I/O system and any questions you might have about device drivers, file systems, abstractions, whatever. So, Daryl?
I found out about 5 or 10 minutes ago that I was going to get a presentation, and I don't have a presentation ready. I have one that I did like last May that's out of date. And so what I'd like to do, I guess, I don't know what anybody knows. Is this being taped?
They didn't tell you that?
Can't we just turn it off for this part? Good Lord. He didn't tell me it was going to be taped on top of it.
Well, we gave you 2 minutes to repair, didn't we?
Yeah. I guess what I should really do is ask the question, what do you know about NT or the I/O system, or how it all fits together, and what do you want to know, or what do you think you know?
We've only learned about kernel, the executive, and that's it.
Okay, so you understand basically how the executive fits together, and I/O system is a component of that, and there's device drivers and file systems, and they all kind of fit in this world, right?
Right.
Okay, and the user API to NT is through NT native system services type things, right? You understand? Okay, and you understand objects and handles to objects and access rates and all that kind of stuff. Okay, good. That makes my job easier. The I/O system, I designed the I/O system to fit into this object model in much the same way as any of the objects in the NT executive. That is to say that a file object is like an event object in that you go out and what you do is you create a handle to an object. Okay, and so
like all the other APIs inside the system, there's an NT create file where NT is, that's what it is, and this is the function that says this is what we're about to do, and this is the object type. So we would have NT create event, NT create process, and there's also an NT open on all of those, and there's an NT open file. What those things do is they create a handle to a file object. Okay? A file object is the object that that represents, if you will, one of a real live physical file, a directory, a volume, or a device. Okay? In essence, what I'm trying to say there is that when you go out and you open a file on the disk, if you use NT open file, what you've done is you've gone out and you've opened an existing object, and we're going to return a handle to it. Okay? Same thing for create. Whether or not what you did when you called NT create file is you actually created a new file depends on the parameters that you pass in the NT create file. Okay? So what we're trying to do is we're trying to say that somewhere out there in the physical world, either on a disk or a terminal or something like that, there is an object, or we're going to create an object, and then we're going to return a handle to it. The operations that you can then perform on the file object get seen as, from the user's point of view, a stream of bytes from 0 to n, where n is the length of the thing that you're talking to. Okay? And that doesn't make any difference whether what you're talking to is a real live file or a device, in which case of a disk, we take the entire disk and we say it starts with byte 0 and ends at byte n, where n is cylinders times tracks times sectors times the size of a byte times the number of bytes in a sector. A terminal, same thing. Right? You go out and you read from the terminal and you write to the terminal. Okay? So we see it as a stream of bytes.
What about a mouse?
A mouse is the same way. You don't read from a mouse. Okay, there are particular types of APIs that you can perform on file objects, and some of them are valid on some types of files and other ones aren't. Okay. For example, we can do an NT read file, NT write file, NT query information set information, et cetera, et cetera. And then, given that not everything in the known universe of I/O fits into this nice, we'd like to be able to read it or write it or query it or set it, like everything else. We have operations that are specific, like query a directory. And then there are some things that don't even fit into that known kind of universe. And so then what you end up with is two services, one called NT device. I always forget when I name this thing. NT device I/O control file. And NT file system control file. And what these guys do is they allow a particular device type to specify a set of control functions that you can hand to the device, which the device then performs based on whatever the function code was, and the same thing for file systems. Okay, so getting mouse events, this is how you do it. You send it in, and these things in OS2 are called ioctls, and we call them twice IO controls or whatever. You send it an IO control that says, please complete this IO request and give me back the data when a mouse event occurs. Okay. Or in the case of a floppy, I would like to do a low-level format. Okay, please format the disk for me. Okay, and it actually goes out and does a low-level format. Okay, so again, the idea is that from the user's point of view, these objects don't look any different than any other object. You get back a handle. That handle has particular handle attributes as well as access rights associated with it. Okay, for example, a file. You have the ability to say on a handle-by-handle basis what the current position in the file that you're trying to get to is, and you can change that, and you can set it, et cetera, based on the type of I/O that you're doing. Okay, those are the API set. If we were to take a look at the I/O system itself, what we'd find out is that, like everything else, there's this API set, which is the NT, what I lovingly call the NT-IO APIs, which are all those APIs, and they get you from user mode into kernel mode, okay? Sitting at this layer is then the NT-IO system services themselves, and they implement those APIs by taking the requests and sending them down into the system, into file systems and device drivers, which are layered in a layered device driver model that then goes out to the hardware. And part of the I/O system defines particular calls and things like that that file systems and device drivers can make to get things done. Okay, and there are a lot of these. Okay, the first thing to say is that the I/O system at this level down is absolutely, positively, 100% asynchronous always. Okay, at the user level, some of the APIs are asynchronous, and some of them are synchronous. And for those that are asynchronous, when you open the file object, you have the ability to say, I would like to be able to say that all APIs that I call are synchronous, okay? Because, in fact, what's actually sitting up on top of here for us is a subsystem which presents an interface, be it Windows, be it OS/2, be it POSIX, or, who cares, Unix, Xenix, or whatever. If you look at every one of those APIs, what you'll notice is that every one of these guys, to its client, I/O is always 100% synchronous. Okay, there are no asynchronous APIs. Well, I don't know of any, there aren't any in these three. I don't know that someone hasn't added some of these, but there didn't used to be. And if you say read, it goes off and it reads it, and when it gets all done, it comes back. So what we did was we gave people the ability to say that what I'd like to be able to do is I'd like to have everything be synchronous. Okay, so what happens is once we come into the system service part of the I/O system, it generates something called an I/O request packet, or an IRP, that represents this request and then sends it to the top level driver, and then that driver takes the request and sends the same exact packet down to the next driver, who sends it to the next one, who eventually gets around to going out and doing something to an I/O device to actually perform this operation. Okay. Does that make sense, everyone? Okay. The I/O system is layered in the sense that between the system service and the hardware, there may be 1 to n layers of drivers. That is, there may be just one simple driver in the case of like a terminal driver or COM driver or something like that. There may be more than one where you're talking to a file system who's then talking to a device driver. There may be more than that in the case where there's a file system talking to a class driver, for example, a class driver that understands SCSI disks, who is then talking to one of several different port drivers based on what kind of SCSI adapters you have on your bus. Right? So if you have a Western Digital and you have an Adaptec and you have an NCR SCSI adapter on your system, that one device driver, the class driver, can talk to any one of those three. And so in this particular case, I've got three layers of driver. I can come along and insert drivers in the middle of here and say I now have a new device driver, and this guy is a striper, or this guy is a shadow driver, or mirror, or whatever you want to call it. Okay, so and you can take a file system, for example, one of our existing file systems, and unbeknownst to it, you can create a tightly coupled volume set And as long as this particular device driver that the file system is talking to presents the exact same interface as the hardware disk driver does, everything just works. So rather than having a bunch of little disks, what this guy does is he presents those guys to the file system as one great big disk, and the file system has no idea that what's under there are multiple physical disks and couldn't care less. Right? And lo and behold, by writing some simple little driver and sticking it in the middle, you end up with a lot of functionality. You can add functionality to every file system in the system by doing that. Just boom, you're done. Yes, sir?
What does the driver look like?
What does the driver look like? Okay. Let me say one more thing about layering, and then I'll answer your question. When this layering occurs depends on what kind of driver you have and what the user gives you as the name of a device. For example, in Landman today, someone can say, I would like to open /server /share /path name, okay? And another way that he might do that is he might say C:. In this particular case, what the user has done to you is he's given you the name of the physical hardware device out here somewhere on the bus, okay? And somehow what we have to do is we have to take that request to this guy and route it to the top guy so that we can then go down, okay? In the network case, what we've done is we are not telling you, whether you're going out on the Etherlink card or the token ring card or something else. What we've done is we've said, out there somewhere is this name, please find it. So we start at a top level guy and we work our way down through TCP/IP protocol stacks or NetBUI or JetBUI or whatever, and then we pick a card and we go out on that card, okay? So in one case you're going this way, in the other case you're coming in and you're starting down here and you have to somehow get up to here, okay? And we can go into that if you'd like as to how we do that. But basically what happens is eventually we get ourselves in a situation where I know that the path through the drivers that I want to go to are, I want to go from the file system to this class driver and out this adapter, okay? The lowest level guy says, I'm at level 1, and when this guy gets stuck, when this guy opens this guy, and he does that just like you open any other file, okay? He says, I get this guy's level +1, and this guy, when he mounts this device on that adapter out there, says he gets this guy +1. And so what happens is when a request comes in, I look down here and I say, oh, the guy that I really want to talk to is here. How many stack locations in the IO request packet do I want to allocate? And the answer is 3. Okay? So what I do is I have these stack locations, one for the file system, one for the class driver in this case, and one for the Western Digital device driver. Okay? I then tell the file system, by putting parameters in here, what the user said he wanted to do. This user said, I would like to go out and read the following data from this file. And so I call the file system and tell him that. The file system can then take that exact same packet, and by placing parameters in here, tell the class driver, hey, go out and read this off the disk. And then this guy calls the Western Digital driver and says, here's the CDB that I'd like to send out onto the SCSI bus. Please go do that for me. Okay? And so that's how we get away with having one IO request packet. Okay. And it can be reused, or we can bust them up, and we may call the file system and say, I would like to go read this in the file. Well, this piece of the file is out there, and this piece of the file is over there, and this piece of the file is over there, and that piece is over there. So what we can do is we can allocate several different IO request packets, all of which have back pointers to the main guy. And when each one of these guys is done, this guy automatically gets completed. Okay. What does the device driver itself look like? It has an initialization routine. Okay. A device driver in the form that we're currently working on is nothing more than a simple program in that it has a main entry point, and that's its transfer address, and its transfer address is the initialization routine. Okay? When we call it, its responsibility is to talk to the configuration manager and go figure out exactly what devices it's supposed to be servicing, okay? It then creates objects for those devices called a device object, okay? And that device object has a name. And all the names of all the objects in the entire system start with that, right? I mean, that you learned before, presumably. By convention, all of the device objects go in the /device directory, and in the case of, let's say, a floppy, there might be two floppies, so one of them would be floppy 0 and one of them might be floppy 1, okay? In the case of hard disks, we might have hard disk 2, and then hard disks in our world are partitioned, and so they have a partition name, partition 3. And that refers to some particular partition on some particular hard disk hanging out here on the bus. Okay? It's its responsibility to go create these device objects with those names. Okay? It's also responsible for going out and initializing the controller and the devices. And it's also responsible for creating something called an interrupt object and initializing and then connecting it so that we understand where this guy's interrupt service routine is. Okay, the next piece of a driver are the dispatch routines.
Hang on, can we just backtrack a second?
Yes.
So that init routine for the device driver not only knows the hierarchy and the namespace that it is going to provide, but also the location of the namespace. Is that correct?
Well, yeah, I mean, we pass it that. But yeah. I mean, it's always going to go in the /device directory. And it's going to, it's going to be some permutation of what you see here.
But it's the device driver itself that defines that as opposed to...
No, the system does. The system tells the driver, which hard disk is this? I mean, all of our disk drivers are going to create device objects /device /hard disk X /partition Y for each of the partitions on that device. Okay? The driver doesn't understand anything about going and finding the partitions. So what it does is it creates a directory here for its device, the actual hard disk, and then it creates /partition 0, and that represents the entire disk, and then it calls the I/O system and says, please go build me a descriptor of where the partitions on this particular disk are, and tell me how big they are and where they start and where they end and stuff like that. And so I go off and I build that, and then from that, it then goes out and creates more device objects, one for each one of the partitions, and names them /partition N.
And the fact that it picked the name partition is knowledge to that device, right?
It's a convention that we use, right? It's a software convention, but if you don't use it, you're going to have interesting problems.
So is there somewhere a standard naming convention for IT? Is it somewhere for most things, for most objects around the system?
Yes and no. I mean, there's nothing that says they have to go in a particular place, right? In order to take some of the existing utilities and port them to NT and make them work, we had to have some way of saying what the conventions were. So for I/O in particular, I mean, what you call your event doesn't make any difference, right? And there's no software convention that says all events end up in the /event directory. There's nothing that says that. Well, I had to come up with some way of keeping track of where all these things were. So we have these software conventions that say this is how the thing works, right? If you wanted to call your keyboard /mumble, you could do that and it would
I
work.
don't really have a desire to call it differently. I do have a desire to find out a place where all the assumed names are given.
Inside the I/O spec is a section on naming conventions in the I/O system, and they basically say this.
Okay. Are there naming conventions for the non-I/O space, for other pieces of the kernel also, where there's
No.
assumed conventions for naming?
Not that I know of. Yep. Okay.
The one thing we tried to do is default on English. I mean, English words as opposed to abbreviations or cryptic things.
No, I don't have any qualms about the names you picked. I'm just trying to find a source for finding the ones that I have picked when it comes time to look.
Right. That's about it.
we don't have very many conventions. The only thing that does have a convention that I know of, off the top of my head, is the I/O system, and that's so that we can keep them straight. And then it's mostly just for, I was going to say mostly just for disks, but that's not necessarily the case. The stuff that sits on top of here that's to Windows, that says C: is that disk, right, is totally arbitrary and is done with symbolic links in the object naming space. The object system presents an object type called a symbolic link. And what we do is we create a symbolic link called /C:, and when the user types C:, or that's his current drive, we stick a slash in front of it, and then we take the rest of the name that the person said, like /temp.bar, and we call the I/O system and we say, hey, go do this. And I call the object manager and say, please parse this and tell me which one of these disks I'm going to, which one of these I/O device objects I want to talk to, and give me the piece of the name that you didn't parse. Well, that, as a symbolic link, points me to /device/ something or other, and so that gets me to the device object, and then it calls me back and says, okay, here's the device object, and here's the piece I didn't translate. I then say, okay, and I call the driver for that particular device, in this case a file system, and I say, here's a name, please go open it or create it or whatever it is that we were supposed to do based on what the person said in terms of NT create file or NT open file. Okay, and it goes out and does the appropriate thing. Okay, the dispatch routines, there's one dispatch routine for every major function code. If we were to take one of these stack locations here and we were to blow it out.
But can I ask a question about that?
Yeah.
That translation, that separable translation, can that operate at different levels of the file system hierarchy? In other words, because I got down 3 levels and I didn't know a name, could you go up somewhere else and interpret that?
Yeah, within the file system, we can have symbolic links. Okay, so there's symbolic links like these object manager symbolic links, and then this whole thing may be this thing right here we may go out to this file and find out it's a symbolic link, and it says, here's a new name, please start all over. Okay, and then we go back to the object manager and we say reparse, and it starts with this whole new name that we gave it, right? In fact, if this were,
do you have hooks in there to do up calls from the file system out to the user space?
No.
To do that?
No, we never do call outs from the user space, to user space from kernel mode. You don't get security ratings doing that. Right. Okay. So if temp if this were a symbolic link that got us to that disk, and this turned out to be a file which was a symbolic link that said, please go to /d:/pickup/ belch or something, right? Then what we would do is we'd take the remaining string and we'd bring it down, and that's the new name of the file, and we'd hand it back up to the object system and say, we didn't find this thing, but we did find this, please reparse, and it would start all over again. We'd take this and find out that's on another disk, and then call us back, and I would give this name to the file system that was handling that particular disk.
And you can keep doing this.
And we can just keep doing that. Yeah, and I mean you can go off node to some other machine, and it finds out, oh my goodness, or you can end up in the DFS namespace or something like that. Right?
Do you have loop counts and stuff like that?
I don't know whether we do or not. I haven't asked Steve what the maximum number is. I presume that there's a number somewhere, but I don't happen to know what it is. And all the name parsing stuff doesn't have anything to do with me, right? I mean, I just take these things and generate packets and tell the IOs and tell these guys what to do, right? Okay, so if we were to take one of these parameter things, I call these things IO stack locations, because as we move up and down through these layered drivers, I keep a pointer to which guy is the current guy and just go up and down, right?
Sorry, let me ask one final question about that. Maybe it wouldn't be final. Suppose I wanted to plug in my own parsing model. how easily could I plug that in?
If you had a file, if you have a, I take,
So again, I get down to
once
some
we
level.
find a device object, right?
Right.
Once I find a device object,
Right.
from there on, everything else is up to the guy that I call to parse.
Right.
So if you wanted to change backslash to pound sign, you could do that.
How about halfway down, sort of, I get to some, I get to C/temp/foo, and then from there on, I want my own parsing scheme.
Within a given file system? Or you want to give me a new name and say reparse and get there that
No, I
way?
want a different parsing scheme from that point, that a different file system handles. In other words, can a file system, in the middle of its parsing, sort of interact with a different file system?
The way you do it is you have a pointer here, you say this is symbolic link to somebody else, and you tell it what to use, and then we parse from there on out. And we have to have some way of getting to you, right? The way you leave one file system and get to another is use symbolic link and say, here's a new name,
Oh, I
go
see,
use
you
that.
just start with a different, okay, yes, I
Right.
see.
So, I mean, there could be pound signs or whatever else
Right.
you wanted out there, forward slashes or, underscores or something like that. And as long as we keyed out there,
And then
Right.
you just put the
then
different
we
thing
just
in
take the
front.
rest of that name and give it to you and say, okay, you parse it.
Okay.
Right? Okay. Okay, within one of these stack locations, within one of these stack locations that determines what it is that we're going to tell this next driver to do, we have parameters that are based on a major function code and optionally a minor function code, which can be altered by some flags. So there is a major function code for IO request packets called IRP under major under read. Okay, and that would be the major function code. And because this is a read, then you take these four parameters and you look up in a union, and you find out that the parameters are the first two long words or the byte offset into the file that you'd like to read from. The next pointer or the next long word is the length, and the next one is a key to use to determine whether or not you own a lock or whether there's a lock conflict. And then there's some other stuff down here that you don't need to worry about for now. For each one of these major function codes, a driver has a dispatch routine if it implements that particular function. Okay, and I guess we have to back up and explain what a driver object is. When the I/O system goes out and loads a device driver into the operating system and calls it its initialization entry point, it has created a driver object. This object describes the virtual, where is this driver? Okay, well, it has a starting address of that, and it has a size of that. And inside of here is a function dispatch table, which the driver, during its initialization routine, fills in the address of the entry points for each of the dispatch routines, for each of the major functions that it implements. Okay, so if I have a driver like a printer, and let's take a real stupid one, all right? It may have an open routine, a write routine, and a close routine, and that's it, for example. What the driver writer would do is it would have three routines: open, write, and close, and when we call an initialization routine, it would fill in the address of those three routines in this dispatch table, and that's all that it would have to do. Okay? Now what happens is when we come into the file system, or we come into the I/O system, and I go to generate one of these packets, I put a major function code in there, and then I call a routine that says, go call this driver at this entry point. If that entry point doesn't exist, these guys are pre-filled with the address of a routine that says, this is an invalid request for this particular device, and completes the request with an error. Okay? So driver writers only need to worry about whichever ones of these things that they're going to actually implement. Okay. Once the driver decides that it's all set, everything looks fine, it's checked over these parameters, it looks good to it, then the next thing it wants to do is it wants to start this request on the device.
and so we have a start IO routine. In the most simplistic driver, what the driver would do is it calls the IO system and it says, here's this IO request packet, I would like to start it on this device. Okay? What the IO system does is it goes to this device, and in here is an MP-safe interlocked queue of requests that has a busy bit. Okay? What it does is it takes out the lock and it says, is this device already busy? If the answer to that question is yes, it simply takes that packet and inserts it into the queue. Okay, and returns and says, fine. So, and then the dispatch routine returns, you know, this is now a pending operation. I'll get around to it one of these days. Okay? If the busy bit is not set, then I will set it and make this the current request. And the way I do that is I say, the current request is now that packet, and I call the start IO routine and I say, okay, your device is not busy, please go do this packet. Okay, go execute this packet. So the start IO routine then says, okay, now I know that this is the only thing I'm doing, and it goes out and it diddles the device, and then it goes and it simply returns.
So it's not the start IO routine that checks for the status of the queue. It's your major function routine.
Neither one of them do. The dispatch routine calls a routine in the IO system that says IO start packet, and says, here's the device object, and there's the IRP. Which, by the way, these are the same exact parameters that all these dispatch routines get called with. The exact same parameters that the start IO routine gets called with. It's the exact same parameters that the interrupt service routine gets called with. It's the exact same, you know, every one of these things has this interface. I'm going to give you a pointer to the device and a pointer to the request. And that's basically all you ever need. Okay? So, he doesn't care whether or not he actually started. It doesn't make any difference to him. Okay, he decides, here, if it's okay for me to go ahead and do this, then call my start IO routine. Otherwise, let's just queue it and forget about it. Okay? Eventually, at some point, I'm going to take an interrupt, and I'm going to call this interrupt service routine, and the object of the primary goal of an interrupt service routine of a device driver inside of NT is stop the thing from interrupting and tell us that you'd like to do some more processing later. So we use the DPC mechanism, right, which you learned about when you talked about the kernel. What it does is it says, diddle, whatever it needs to do to make that thing stop interrupting, because we're now running it at the same IRQL, interrupt request level, as a device. So we're way up here, we're blocking interrupts all over the place, nobody underneath us can do anything, right? We go out and we diddle the device and we say, okay, queue a DPC and execute this routine the first chance you get, okay? And then it exits. I mean, it just returns, okay? And we return from the interrupt, and if nothing else was going on in the system, we take the DPC right then and there, okay? We then call the driver's DPC routine, and its functions are three things. One, go out and figure out whether this thing worked or not. Two, complete this packet, that is IO complete request. It calls the IO system and says, this request is now complete, and then it starts the next packet, IO start next packet, and it says, here's the device object, and here's the IRP. And it exits. It's done.
There's a couple of things. First of all, do you support multiple hardware priorities?
Yes.
In which case, how many? And also, does that have to match directly to the hardware itself?
Yes, we do. The answer to how many depends on the type of machine you have. On the x86 today, I think that we're currently running downstairs with like 36. On the i860 machine we were doing, we had 4. And how does that match NT? You define what the functions are going to be based on what kind of processor you're executing on.
So in other words, you do a virtual mapping, effectively, from the hardware to a software level.
That's right. That's right.
And the other thing is that the DPCs, do they run at an elevated hardware priority, or do they run at effectively?
IRQL 2. Dispatch level is equal to 2.
The DPCs always run 2. Is there any prioritization of queued up
FIFO.
DPC work?
FIFO.
Okay.
Question on your IO start next packet call.
Mm-hmm.
that must call something back inside the driver.
Yeah, what this does is IO start next packet says, go out to this device object, and if, obviously the busy bit is set, right? If there's something in the queue, then pull it out and call it start IO routine.
It's the same start IO for...
It's the exact same start IO. It says, okay, here's another packet, start this one. Okay, we're all done with the previous packet, right? We just finished it. Now let's go start the next one.
Okay, so the difference in context between we're telling a device to process the first packet of the day or the next packet of the day, you're seeing the take care in the init routine. Start IO was also called when you sent the first packet. to
Yes,
the device.
what's the difference between the first request we ever give you and the second one?
Some devices can make a difference.
Then what you'd have to do is when you get to your start IO routine, you'd have to look in your device object. Every device object has an optional extension, which is where you keep all of the read-write data that you want to keep around in the context information and state information for your particular device. Presumably, you'd set it and say, I have not received, that's a 0. I have not received my first packet, and that's the way you do in the init routine, right? And it's possible to do something slicker than that. I won't say that I said this, but because you're synchronized when you get to the start IO routine, and you know you can't get to the start IO routine again from any processor once you get there, because now if someone's got another request, you're busy, so it's going to go in the queue. You could, theoretically, go change the address of the start IO routine to some other start IO routine. You'd have one for, hi, this is the first time, and one for, hi, this is every time thereafter. And I mean, the start IO routine's address is in the driver object, right? I mean, you could do that. I mean, it's pretty backhanded, but I mean, you could do it. If there's anything that I can say about this IO system, it is that it is absolutely 100% flexible. And you can do just about anything. I mean, we've got disk arrays that can take, multiple packets, in which case you don't serialize the IO, right? What you do is you get the thing started, and then as requests come in, you ask yourself, is the device busy? Yeah, well, you just queue it up. You queue it up, you queue it up. Now the device says, I'm done. And you go, okay, great. Take everything that we've accumulated since then and hand the whole thing to the thing, right? Or whatever you want. I mean, you can invent anything you want, right? We've given you all the low-level primitives, and they're all MP safe, and they're all re-entrant, and on and on and on. They're all synchronized and everything, right? And you can use them in any way you want. And we've used them in some pretty imaginative ways in order to do some of these brain-dead devices. Like, I mean, take these floppies, right? I mean, these floppies are, you go out to the floppy and you say, okay, here's 1 byte of this set of command bytes I'm going to give this floppy. And you ask the floppy, are you ready to receive this byte? No. Are you ready to receive this byte? No. Are you ready to receive it? I mean, you can go up to 375 microseconds later, and it's allowed to go that long before it says, okay, I'll take the byte. So you give it to it, right? Okay? You got 8 more bytes you got to do this with, right? So you get the second byte and you go, are you ready to take this byte? No. Are you ready to take it? And you just go through this forever and ever, right? Okay, well, you take 375 microseconds, and you multiply it times 9, and you tell me how many users are going to like the throughput of your machine now, right? Because you've hogged the processor going, can you take this? Can you take this? Can you take this? I mean, that's stupid, right? So, I mean, we have ways of dealing with things like that. Like, for example, your device driver can have a thread associated with a full-blown thread, right? So what happens is when you come in here to your dispatch routine, you go, hey, it looks good to me, hand it off to the thread, right? And the thread wakes up, you context switch to him, he wakes up, he goes out here and he tries this a couple times and says, I'll talk to you later, right? And he goes into a wait state, right? He actually waits in the thread, right? So you go back and you do some real work until it's time for him to wake up. 10 milliseconds later, and he says, now are you ready to take it? And so he says, no, I'm still not ready to take it. He says, fine, right? And so you go back to sleep for another 10 milliseconds, and then you wake up, and if he tells you no this time, it's definitely been more than 10 milliseconds, right? He has the 375 microseconds to say, yeah, and you say, hey, you're screwed, man, forget it, right? You time out the request, and you say, this request didn't work, and you complete it with an error that says, I got a device timeout. This thing ain't ready to do jack beans. Either you don't have a floppy in there, or else something bad, really bad happened. don't get me going like that, okay? I get too sweaty. Okay. And in fact, not only can you have threads, but you could also have processes. I mean, a full-blown process with an entire, 2 gigabytes of its own virtual address space, and you can create threads in there, and now I can tuck information in there. I mean, local cache information. It's obviously easier in a network driver to cache information in a 2 gigabyte virtual address space and context switch to it to get the data to give back to the user than it is to go down through a bunch of transports and actually go out, give you the thing up into 1,536 byte messages and send it out on the Etherlink, wait for the other guy to get it off the link, go up through the transport to the server, through the server, through the file system to the cache, and then all the way back down again, right?
So if you do create a thread as part of one of your device drivers to deal with some slow device thing, then that thread is going to be essentially an executive thread.
Mm-hmm. It's a system thread. Runs in kernel mode only. Can never go into user mode. If it does, you're going to keep the sneakers.
And it's preemptible and all that good stuff?
It's preemptible. You can set its priority. Generally what we do is we set the priority of those kinds of threads to the lowest real-time priority. Right? So we set it to 16.
You built one of these things with a floppy, with a 995 floppy disk controller, and it all works?
Yeah.
And so this
Yeah.
thing
Well, we use 82077, right?
right, so the system
yeah.
is reading a floppy,
Yeah.
and people are still can do.
Oh, absolutely. Oh, absolutely. Yeah, absolutely. Yeah, it works out pretty nice. I mean, it's a lot better than the BIOS stuff that we have today. I mean, you get into the BIOS, it actually does just what I was, saying. I mean, it's pretty disgusting. The first time I ever looked at the code, I went, no, this can't be right? No. I mean, these things in this world, to me, having been in this world for 2.5 years now, after spending 16 years in the real world, sorry, I mean, like the first time I programmed this thing, it took me 2 days to write the floppy driver, and it took me 2 days because I couldn't believe that the thing was so brain dead, right? I could not get the thing to successfully complete a request. You know why? Because what you do is you go out and you say, I'd like to start reading data at this sector, and I'd like to end at this sector, right? Well, it goes out and it starts reading, and after it's read, and you also tell you tell the DMA controller, not the device, you tell the DMA controller how many bytes are about to show up, right? And as soon as the DMA controller sees that many bytes, it goes out and says, hey, stop transferring, right? And the floppy says, hey, whoa, I got an error, you told me to stop transferring, right? So it gets an error. That's case number 1. Case number 2 is it can only read a track at a time, and if it hits the end of the track, it gets an error. It says, hey, I hit the end of the track, right? Why didn't we just tell it how many bytes it was supposed to be transferring? You look like it incremented up to 0 or decremented down to 0? Wrong. Okay, anyway.